Good afternoon, everyone. I am Priya, one of the organizing co-chairs, and I welcome you all to the second day of week 6 of IEEE Symposium on Data Analytics and Internet of Things. IEEE Victorian section presents the symposium in collaboration with Computational Intelligence Society, IoT Community, and University of Melbourne Student Branch. Just to quickly run you through the schedule of the symposium, it's going to run for 2 more weeks until 19th of November, with events happening only on Tuesdays, Wednesdays, and Thursdays, either as afternoon or evening sessions. Since you're registered for this week, you will be on our e-meeting list and will receive emails about the event schedule for all of the following weeks. You can also follow our website and social media pages for more updates. So today's talk is applications and advancement in smart health. The talk will be for around 45 minutes with last 15 minutes dedicated for question and answer session. Please use the question answer tab at the bottom of the window to post your questions. So we have Professor Sanjay Ranka as a speaker for this event. Sanjay is a professor in the Department of Computer Information Science and Engineering at University of Florida. His current research interests are high performance computing and artificial intelligence for healthcare and transportation. He teaches courses on data science, data mining, and parallel computing. From 1999 to 2002, he was a chief technology officer at Panama, California, where he developed a real-time optimization service called Pilot for marketing campaigns. He's also a fellow of IEEE and AAAS and a past member of IFIP Committee on System Modeling and Optimization. Thank you, Sanjay, for joining us today. The floor is all yours.
Oh, thank you. Thanks a lot for the introduction. So my intent today is to give you a brief introduction to a project which we are working on. The project is called ROAMM, and the key idea is around using wristwatches for understanding health events with a focus on elderly population. This project is done jointly with a lot of people. I'm going to just try to see. I'm sorry. Okay. So the two people who lead this, Sanjay Manini is my co-PI. We have several other investigators from biomedical to healthcare, and number of PhD students who have worked on this in the past and are currently working on it, along with several staff members. Our main goal is at a high level to say, hey, wearables are going to become more and more popular, and they can be effectively used for mobility monitoring for older people. In particular, older people have a challenge that as they get old, if their physical abilities go down, their quality of life suffers. And our goal is to see how that progresses and also look at a variety of other issues which happen. So what I'm going to talk today about in that context is how wearables can help in monitoring, in assessment of physical activity, in activity recognition of what they are doing, in a lot of self-management applications for chronic diseases, nursing and home care, base care, and also in healthcare education. There are lots of technical challenges, which I'm going to talk about. Wristwatches have a limited battery life, and obviously we want to be able to capture as much information as possible every day before the patient goes to sleep when they recharge the watch again. Also, wristwatches are new to the game in terms of measurement of activity. The gold standards in this area are hip-based accelerometers, so we want to talk about that too. And the last part is there's a lot of interest in physicians to understand how their patients are behaving, what kind of pain, anxiety they are feeling throughout the time. So there's a lot of importance paid now in terms of patient-reported outcomes. You send a patient after surgery, you want them to be able to keep track of their pain levels, because when they come back to you in a week, they may have forgotten how painful it was. They'll tell you today is really bad. I don't remember what happened 3 days ago. So keeping that in mind, we started this project roughly around 3 to 4 years ago. And we were thinking of us looking at very specialized devices to capture this. One of the problems with the specialized devices is that you send the device with the patient, collect the data, they send it back to you in 6 months, and then you can analyze the data. Now, lots of these devices have been built with very low battery requirements so that you can collect data for long periods of time. The challenge with these devices is that they're not very interactive. You only get the data after 3 to 6 months, and you don't know what kind of events have happened during that time. And for a variety of reasons, if, for example, a patient who's wearing a device takes a bath and the device stops working, all your effort to recruit the patient as well as collect the data is all lost at that juncture. So we thought that, well, why don't we look at something which is going to become more prevalent? Smartwatches were coming on the horizon, and they were having more and more of these devices. Our firm belief is that just like a smartphone has replaced cameras for most people, a smartwatch will replace effectively all kinds of sensors which are there, which people use for measuring a variety of things today. Will converge towards a smartwatch, or a smartwatch will become a hub to collect information from a variety of wearables. It could be, for example, if right now you can't say measure blood pressure, and there's a blood pressure monitor which can connect to a smartwatch and keep track of your blood pressure at a regular interval. If you have hypertension, for example, it's very important for you to measure your blood pressure regularly, especially if you're an elderly patient above 70, 75, where you have lots of variations from day to day in your blood pressure. It could be pretty dangerous. It can impact your kidneys and things of that nature. So the other important part for us was that the connectivity should be there throughout the day. Why is that important? If you look at many of the devices, they will only work when you're at home. So if you're connected through Wi-Fi, you can collect a lot of information. But as soon as you get out of the house, then you can only passively collect the data. There are challenges with that, because we also want to look at how elderly people behave outside the house. How much are they walking? Which all places do they visit? Are they driving? All that tells us a lot of useful information about the patient's overall social behavior. And that's also very important. The good part is lots of watches are being sold, 20 million in the US last year. You can multiply that by a factor of 10, 20 throughout the world, and the numbers are only growing. The other advantage is, unlike smartphones, where a patient can actually enter data just the same way as a smartwatch, as you'll see, we can collect a lot of passive information which you may not be able to collect from a smartphone. You don't always carry your smartphone in your pocket. You may leave it when you're doing some work, or you may leave it in your car. And at that juncture, we cannot track activity anymore. The other part is the smartwatch is not directly connected to your body, so you cannot collect things like pulse and in the longer term temperature and blood pressure that easily. Someone has to enter it. And if someone has to enter it, you suddenly start having compliance issues where you don't get information about all the time, only when they actually enter it. The other part is that people like wearing watches anyway, and as these watches become more and more fashionable, the earlier versions were very kludgy, and people say, oh, this is a bulky thing, I'm not going to wear it, but the newer ones are becoming more and more fashionable to wear. So there's a big market, and our goal basically is to say, hey, once everyone has a smartwatch, we can generate an app which we can use to collect data from a larger population. Although the focus of our work right now is more towards patient studies of a limited kind, where we are sending watches to 100 to 500 people for doing a study. That's what I'm going to talk about. Now, the other important part, as I said, was that besides the sensors, you do want to make sure that there's connectivity. And most of these watches now can be independent of the smartphone. In the previous generations, they had to be tethered to the smartphone, and they would not work effectively. So what are our goals? So our goal is to build this wearable technology infrastructure based on this ROAMM framework to capture domains prior to and following intervening health events. Now that's very important, because what you're really saying is the following, that when you go to the hospital, At that juncture, the event has already happened. Say, for example, you had a fall, had to be hospitalized. You don't know what led to that event. And if you want to be able to predict that event, you need to have data before that event happened. For two reasons. One is you want to understand what led to the event. And the second thing is once you collect data on a large number of patients, in the long term, you can actually prevent that event to happen. So for whatever reason, if your watch figures out that, hey, you're going to lose, your BP is going down rapidly, and at that juncture, you may fall with a high probability, it may say, hey, please find a place to sit down so that that event doesn't happen. So that's an important part of having continuous monitoring. And that's the good part about having watches because they have connectivity 24/7, at least till they have battery. So the focus of our project is on broadly four areas. One is to look at wearable technology, and I'm only going to talk about watches today, but at the end of the day, we can actually extend this to other wearables. And we look at VR, software, server, hardware. And then from a data science point of view, we look at machine learning, data security, cloud computing. From a domain point of view, we want to look at these four domains of importance. And then we are obviously interested in all these clinical outcomes. So our goal is to be able to look at all aspects of healthcare to be able to capture useful information. Now, as I was pointing out to you earlier, the key part is that event happened here. Suddenly, their mobility went down. Say, for example, they had a fall. And this is something which people have noticed time and again that they are going to, if there's no intervention right away, then at that juncture, the mobility keeps going down and the health suffers and the quality of life suffers. Or something was intervened right away, still there's some amount of decrease with age, which happens all the time. And if there was no health event at all, then in that case, the mobility will slowly decrease over time. And we're only talking about here in terms of years, right? And this graphic is just to show that the mobility is decreasing over time, but after a health event, it decreases below normal. And the key part is it's possible that something which we can collect before, which will tell us that this event will happen so that we can predict it and then try to make sure that we can address it. So what you do is, if an event happens, you can compute a baseline. You can compute a baseline after the health event. You can do it after 2 weeks, 3 weeks. And this is the kind of thing which you can actually use to understand the impact of those health events if you have data from a large number of people in your study. Any questions so far? All right. Okay. So what is the purpose here? We want to be able to leverage all the sensors. The key sensors which are available today are what are called triaxial accelerometers, heart rate, temperature, gyroscope, UV exposure barometer, GPS, GSM for bidirectional communication. These are the sensors available today, but our expectation is that we are going to have a lot more sensors. And then we have patient-reported outcomes, and I'll talk a little bit about other things which we can do in terms of cognition tests and medical outcome reporting. So our goal is to be able to look at all of this. Key focus being community mobility. That means how are people walking around their community? Activity, what kind of activity are they doing? Are they doing brisk activity, walking activity, playing golf, for example? Patient-reported outcomes in terms of, it could be what they call EMAs, where I can tell you and say, hey, what's your pain level right now? Are you feeling fatigued? Did you have a good sleep last night? These are the kind of questions which can vary based on the study you're trying to do. And then I can test your cognitive abilities at a regular basis. Then you have intervening health events when they happen. Then I want to be able to measure that, what happened which led to that event. And then, in fact, at some juncture, I can even call you and say, hey, you're going to have this event, take care of this because you don't want to fall. Or if a fall happens, at least if I call you and say, hey, maybe you should do this particular intervention so that it can help you with your fall. So what we do is we compute a variety of things. We can compute total activity, categorize them into different categories. We can compute what is called walk speed. Walk speed. Walk speed is kind of a gold standard for older people. So generally what happens is if you go to a aging facility, they'll make you walk around for X hundred meters, and they will actually measure and say, hey, how long was the walk time for those 200 meters or 100 meters. And that tells you a lot about the person's overall ability in terms of what their quality of life is. So the good part is, since we have GPS, if someone has gone for a walk outside, we can actually measure their walk speed. They don't have to come to the lab to measure walk speed anymore. And at that juncture, we can keep track of it in a temporal fashion. We can define what's the life space. Life space is kind of a mixture of activity and also how far are you going. So for example, in this case, if I was located at the center of this ellipse, it's showing that I'm going 10 miles in each direction on some days, and 2 miles in the other direction. So it gives you both the excursion size, that means how far did you go or how much did you travel, but also some idea of, radially speaking, how far are you generally going at a regular basis. It tells a lot of useful information. If your life space is small, it tells you that you're really sticking to home, while if your life space is larger, that means you're physically fit or you're socializing more. What else do we want to do? We want to be able to measure pain, mood, fatigue. So what happens is you can set up this watch. This is actually a physical copy of the dial which you're seeing right here. And the person can rotate this or touch this depending on the watch and say, hey, my current pain level is from a scale of 0 to 10. You can push 8, 7, whatever you want, and it shows what that value actually means. Or it could be discrete values, or it could be numeric and say, are you having difficulty climbing stairs? And the answer would be yes or no. So these are all different kinds of questions which you can program the watch for, and I'll show you some details on that. The other thing which we can do is we measure cognition. So we can say, hey, based on, I'll ask a question, and depending on your reaction time, I can figure out what's going on. You can see a shape. Whenever you see that particular shape, you need to press a button. Or you can do what's called forward span. I'll give you a series of digits and then ask them to repeat it. I'm sure you've heard Trump repeating these 4 digits many times to show that he's really smart. But this is a basic test which has been done many, many times for elderly people to make sure that they are effective in their cognitive abilities. And then you may be given a series of digits and asked to repeat backwards. So the good part is, the more you can automate this, the more you can keep testing this at a regular basis and effectively make changes in their behavior through interventions. I'll give you an example of that, right? So this is a forward span test, which basically says, hey, the audio script says, I'm going to say some numbers, listen carefully, and when I'm done, say them right after me. You will get 15 seconds to give your answer, and then we'll get another set of numbers to say. So the way it works, and I don't really know how the audio will transmit over Zoom, but let me give it a try anyway. Can you hear the audio?
No, we can't hear it.
Unfortunately, yeah. So that's the problem with Zoom.
Yeah.
But all it's basically saying is exactly as the script is saying, that I'm going to say some numbers. So the audio recording comes in, and then it says, please repeat the sequence. And at that juncture, the person speaks it. We use VR technology to match it and then ask for the next sequence. So you keep on asking the same question 3-4 times, and then you collect the data. And right now there's a high quality VR technology which can convert your voice into the recording. Or if not, a nurse can listen to it and say whether the person answered the question correctly. So we keep a recording of whatever we. The other question which you can ask is intervening health events. Even if did you have a fall? Many times older people fall and it's hard to detect it because they just, fell off. And they were getting off from the bed and they just had a small fall, maybe hard to detect. In that case, you can keep on asking this kind of question and say, hey, did you have a fall last week? If yes, what day did it happen? Did you need medical care? So this kind of regular checks, you can keep on programming them. So the key part is that you don't want to customize this for every study. It becomes very challenging to be able to do this for every study. So we want to be able to use the system for a variety of studies. So we want a configurable system. The idea being that if you are a researcher who wants to study pain, in this particular case, for example, you want to collect accelerometer data, you want to collect user-reported outcomes and pain, then this watch should only be asking you questions related to what you care for. Another researcher wants to collect GPS data to compute activity and then also reports outcomes based on activity, then it should be more focused on this. So the idea is that this should be configurable based on your needs. In every case, what we do is we collect the data and we send it to the cloud environment, which is highly secure. We use Amazon Cloud, although much of what we do can be done on a Google or any other cloud system for that matter. The system also allows you to run multiple campaigns. So you can have one study doing pain, another study doing activity, third study doing something else. It doesn't matter. This system can support tens of campaigns at the same time. And each watch is assigned to one campaign. So this is the way it works. A campaign design has what kind of data do you want to collect? You can configure the sampling rate. You can configure the collection frequency. You can collect the features constructed from raw data. You can do cognitive tests. You can do these 3 or 4 different tests which are around. You can collect responses. You can define what user outcomes we want. At a broad level, we support 2 kinds of prompts. Either the prompt has many values or discrete values, like, for example, in this case, what activity are you performing, or numerical value, which is continuous 0 to 10. So we can do both kinds of prompts and what kind of question should be displayed with that. So then what happens is, at that juncture, if you want to define a campaign, and I'll walk you through a campaign definition, you'll see that on the screen. Basically, it'll show you what actually happened. So in this particular case, for example, you create a new campaign called campaign 98. You ask the question which is going to be on the UI, but on your watch is going to be very small. So you'll say, what's your question? What's the minimum value? What's the maximum value? You can set your anchors, and then you can define one to be low pain. And so effectively what happens is when you dial that number, it will automatically show that up for you. So so between 1 and 4 is going to be low, and 4 and 7 is going to be medium. You can tell precisely what times you want these prompts to be displayed at a daily basis, and also choose a particular time. Then at that juncture, you pick up another one. In this case, you're picking up activity. You set that value, and the same procedure you follow in this case, and at that juncture, again, in this case, you're defining sitting, standing, walking, things of that nature. You can also assign images to them till the images are of a particular size. The system is also smart enough to figure out that if your prompt is too big, then it's not going to work. So it'll say the maximum number of characters are 10 or 15, and if you go beyond that, it won't let you do that. And these are the cognitive prompts which are preset. You can set the sensors and say what frequency do you want to collect the data, because again, your goal is to save battery life. You don't want all sensors to be on for your application. You can choose whether you want GPS to be on or not. You can at this juncture, it's showing you all the thing, and you create a campaign. Generally, as you can see, this was obviously done very fast, but you can in 15 to 20 minutes, you can define a campaign. And at that juncture, it will effectively start collecting data once the campaign is started, and you can start looking at data at an individual level or an aggregate level using an UI. And you can compute all kinds of other features which are typically important from an activity point of view. I'm not going to go into the details of these, but these tell you a little bit about stance, total activity, what's your battery of your watch, did it go down, how did it decrease over time, all kinds of useful information which you can use then both from a patient point of view, and then it'll tell you where did the patient walk. So it'll tell you effectively the overall activity of the patient, where all that person was there in the last day or last week, depending on what you are interested in. And then you can download the information in a place which you can then use for more detailed analysis. So this is the raw data which you can kind of get to analyze. So that kind of covers the overall UI. The good part about this is that this is not specific to a particular study. You can use it for multiple studies. Overall architecture, the way it works is the campaign manager first creates a campaign, just like what I said. You can register participant, assign each of them watch, and then as soon as you do that, you give the watch away. The data starts getting collected on Amazon. Amazon is a Lambda service, which as soon as you get the data, it stores it in a Amazon DynamoDB, or a relational database, depending on what you need. You can export it, you can analyze it using a visualization interface. So you can get both raw data and use our visualization interface. We also wanted to make sure that whatever data we are collecting is actually useful from a healthcare perspective. So we have done a lot of testing in terms of saying that, hey, why don't we measure it in the real world versus what the watch is measuring? And so we've done a physical activity test, walk speed test, excursion distance test, EMA, by actually feeding in values and keeping track of it to make sure that the watch collects the right data which is useful for you. Let me take a break and ask if there are any questions which I can answer before I move to the next step. Anyone?
Do we have any questions?
Okay. All right. So right now we support both Samsung and Apple, and we have actually given the watches out to people, done a questionnaire focus group to understand whether they like wearing the watch or not. We are doing this study right now so that we will get some feedback from actual users. But the general idea is you do a visit, do an assessment, return watch after you do the assessment, and the whole idea basically is that once your group size is large enough, then you have some ability to understand how people are actually able to use the watch. Remember, we're talking about 70 to 80-year-old adults. Many of them have reading issues. We want to make sure that this is going to be useful for 80–90% of the patient. Some people have issues with listening, so we cannot always do some of the cognitive tests because the volume is too low. Also, we try to keep the font size to be reasonably large, but clearly some people have vision issues also. The next phase, which we are starting to work on now, is to actually do studies ourselves, and then there are 3 or 4 other groups which are using our watch, one at Yale and one at a few other universities, which are going to try to use our system to collect data for their study. Now, this kind of covers things from a healthcare perspective. Let me tell you a little bit more detail about the technology and the machine learning under the hood to be able to develop this stuff. So the way this thing works is that all of this information is collected on the watch. We don't actually transmit the raw data to the cloud, although we can. because then at that juncture, you're using a lot of data bandwidth. And if you have a data plan which costs you lots of dollars per megabyte, then at some juncture that becomes cost prohibitive. So our goal is to be able to compute the right features right here using the watch CPU and only send compressed information. Also, in some cases, having raw data at a 10 hertz level is not very useful. You want to be able to aggregate that data at a 5-second, 15-second level, because practically that's all is really useful for your application. So we control that. And all this data goes to an application manager. We store that in a cloud system. This is showing Spark, but we use Amazon system now. This is somewhat older slide. The technical challenges, as I said, depending on what sensors you're collecting, if you're collecting this at a 1 hertz level, then this is the size of the data which you are generating. Now, in today's day and age, a megabyte is really not a lot of information. But again, remember, this is running for 10 hours, you need to multiply this by 10. And this is telling you what happens if you do it at a per hertz level for 2 hours. So clearly, it makes sense to aggregate that. So we compute a lot of online features. We compute what's called a vector magnitude. It gives you the directionality of the activity because the accelerometer is 3-dimensional. So it gives you acceleration in 3 directions. We use that to compute the vector, which is effectively the square root of one direction plus square of second direction plus square of third direction, and also the directionality of that vector. Both of them are useful information. And we generally collect 15-second epoch data in most cases. We compute time domain measures, frequency domain measures, orientation measures. These are standard things which we do. So most applications actually can be built using just this. Of course, you can get the raw data for testing purposes. The good part then is that you can control the battery life. So if for example, we have done battery life measurements. If you're doing it at 1 hertz level, this is the battery consumption. Obviously, if you do it at a 0.1 hertz level, the battery consumption go down by roughly a factor of 5 to 10. Not exactly 10, but quite a bit down. So these are things which we have studied. And one of the things which we have done is we can actually say, hey, if you are not wearing the battery the watch, can we detect that? So that at that juncture we can shut off all the measurements because there's no point measuring it. You're taking a bath or you are going to sleep. At that juncture, you've taken the watch out. There's no point at that juncture worrying about that. So we have developed machine learning algorithms which will automatically detect whether a person is wearing the watch or not wearing the watch. So the way it works basically is you can use GPS or you can use heart rate monitor, both, depending on what you want to use. We have used both of them. But the good part is that the cost of the heart rate monitor is a lot cheaper in battery life. This is every 5 minutes. This is every 60 minutes. It checks and see whether you're wearing it or not. If you shut it off, then it checks again after 60 minutes. So obviously you may lose data for up to 55 to 59 minutes if you set up a 60-minute number. If you set up a 5-minute number, whenever you start wearing it again, it'll check up again at that juncture and figure out that you started wearing it and start collecting data. So the key part is not only is it useful to develop these algorithms, but having a good understanding of what sensors are useful in prediction and how much energy do they use combined together is useful in making your overall decision. We can look at activities. We can compute. We have looked at this data. We look at accelerometer information, pre-process that, compute DFTs and other features, and we can get an accuracy of around 97% with an F score of around 93.73, which is pretty good. So this is only tells you whether you're sedentary or non-sedentary. Again, all of these computations can be done on the watch, so that the server is only doing a small number of things. The good part about this is that you're reducing the bandwidth, but obviously it costs in terms of battery life, although the computation battery life requirements are very, very low compared to the sensors. We have done physical activity detection or assessment. The way it works is you can compute all these features, which are standard features, which are available in the aging literature when people are using hip-based accelerometers. The uh, the we can actually look at that. There was one question which was asked, which I just noticed that, and let me go over that. It says that pain measure is subjective. Why not develop an objective measure? Yeah, people have been trying to do that, and I'm no expert in this area, so I would refrain from answering it. But generally, the problem is that it's hard to say, even two people in your own family, some people can bear pain lot more than other people, and it's hard to say, well, a pain number 5 for X is going to be the pain level 5 for another person Y. All you hope is that the same person, when asked the question multiple times, when they give answers, their grading is going to be somewhat relevant. This is a challenging thing, which we have talked to pain experts. I'm not an expert in this area, so that's all I can answer. All right, so you can apply machine learning methods at that juncture. You can create new measures. Our goal is twofold. One is to do physical activity, but also to compute what's called energy expenditure. This is the energy you expend by walking and doing activities during the entire day. And this has a high correlation with the quality of your life, as well as the aging deterioration which happens over time. If you don't walk around, both the size of your muscles go down, as well as their strength goes down. And there are terms for that, and we study those things very carefully. And they are all related to actually how much activity do you have. So we, just like what I discussed before, we compute all these different standard risk measures. But what we then do is we apply machine learning techniques. So we'll take all these activities and break them into smaller epochs of some k seconds each. Use machine learning to derive what's called a code book of all the different, if you may, waveforms. And then you can go back and say, hey, walking generally has these waveforms. This is called a bag of words model. And computer work has this one. Sweeping has this one. And then once you compute that, then you create these feature vectors. And then when you have another person doing the same activity, you can go back and say, is it closer to walking or computer work or sweeping? And then you can start predicting which is the activity they are closest to performing. And using that, you can compute how much energy they are actually spending. So the details of this, the way it works is, first you take this data, break it into smaller sequences, then these are subsequences. Then you take all of these and you cluster all of them, find the centroids of the clusters or representatives of the clusters, and then you derive what's called the code book. And then once you derive a code book, you take a new activity, you again break it down. And remember, different people have slightly different walk speeds. So you want to be able to take that into account. So rather than, and then also depending on when you start, when you break it down, you may break it down at different points. And so depending on the sub pattern which you're looking at, you may get different portions. So you need to do what's called dynamic time warping. And once you do the dynamic time warping, you get a matching with a codebook vector. You obviously want to give less importance to activities which happen more frequently. And at that juncture, you have this vector right here, which can help you figure out what category something belongs to. So then from there, you can actually compute once you have the activity and other information, you can compute the overall assessment and try to understand how much energy consumption is made. Because rather than directly computing energy from the raw data, once you figure out the activity, you can actually show that your overall resultant energy computations are a lot better. So there's another approach, which is a variation of that, where you take every person and every activity and figure out the motifs. And then you develop a code book separately for each person and each activity. And then you take the activity for every person, combine them together into finding unique patterns for each activity, and then deriving the code book that way. In this case, in the previous case, you were just mixing them together and applying an unsupervised approach. This is a little bit more supervised approach. And what that happens then is that you need to figure out these motifs. And so we have algorithms to determine that this particular activity can be, for this person, can be broken up because this is similar in nature. You are seeing the same patterns. You find out the key motifs for that person and that activity, and use that to build your code book. So what happens is, once you get these code books, once you get these clusters, you cluster all of them together, you take the centroids, and that becomes your representative code book. And then you can use that to, so for example, this is the code book which we derived using around 40 patients or so. And then now what you can do is, you can take every activity and map it into one of these 32 code book vectors. And what you get is that the atoms for sedentary are like this. This has been mapped to a two-dimensional space from a visualization perspective, although the actual value is more of a vector. And then you see that the atoms for locomotion are in different places. So what happens basically at this juncture is, what you're saying is, hey, the clusters in your space which you have mapped this to for sedentary behaviors are different from locomotion, and so you should be able to better classify them. So we have evaluated this on data from 146 people in a large age group. We computed different physical activities. This is data collected by a variety of users at University of Florida, and then we derived features using the standard features, and also looked at bag of words and supervised shape features both together, and computed physical activity that way, both in terms of recognition and the actual energy which was estimated. Now, this was done in a lab environment, so you actually had real measurements both of energy as well as their physical activity. So this data is labeled. And so you can see that essentially all the three models performed reasonably well, although when we look into the overall accuracy, we generally find that the supervised shape model seem to be much better than the other ones in terms of two categories, standing versus sitting. And when you add more categories, then it actually does even better, because since you were training it specifically for every activity and every person, it seems to be able to do a better job in classifying the activity which you're doing. So this is the results in terms of the actual energy estimation. You can see that although the activity was recognized very well, generally speaking, the root mean square errors were not very different. I think these are not statistically significant. But if you can, this graph is much more useful. These are all the different activities that you have performed, and this is for each activity, what was the calculated value and what was the actual value. And you can see that most of our results are pretty accurate within a small zone. These methods seem to work very well. Just list of some publications. It's around I guess it's around 12:47 your time. But this is a collaboration between computer scientists and domain scientists. We integrate edge and cloud computing, leverage machine learning and AI, and our hope is that it will generate lots of novel applications in healthcare. This is just a synopsis of the work. I'm happy to answer questions at this juncture, but all the papers should be available on the web. We'll provide you more details on machine learning as well as our architecture.
Thank you, Sanjay, for the great talk. It was very informative, and I'm sure everyone found it insightful too. So for the questions, we have two questions here in the chat. If the user moves from Apple to Samsung phone or vice versa, would the data integration between two devices be possible?
Yeah, so our goal is to support multiple devices. And so we uniformly store the data in the same way. But obviously you have to understand that there are going to be differences between patients using Apple versus Samsung in terms of what data they can provide sometimes. But from a technology perspective, we are agnostic. We can actually have a study in which we do both.
Okay, thank you. The next one is I've heard about smart shoes and pendants in the market with similar functionalities. Can you please elaborate on how how smart watches serve better than these devices for ROAMM applications?
Can you repeat the question one more time? I'm sorry.
So she's asking, there are smart shoes and pendants available in the market which have similar functionalities. So, how do the smartwatches serve better than these other devices for ROAMM applications?
Right. So several things, right? One is bidirectional connectivity, right? So you are constantly monitoring. In those devices, you cannot monitor people, right? Those are only collecting data. They don't have any communication mechanism. All the smartwatches have a GSM which goes through your satellite, and you can collect data in a real-time basis. If a person is going to have a fall, we can actually call them and say, hey, you're gonna have a fall and better watch out. Or if the person is not wearing a watch, we can call them on the watch or their home number, whatever the case may be. So in many of these sensors which you talked about, you don't get that level of either accuracy or the variety of sensors or the bidirectional connectivity or the real-time nature, depending on what particular device you're using. For example, if you're using Fitbit, all it will do is it'll measure your data over time, and then when you connect it to through Bluetooth, then it'll download the data and give you some number.
Yeah, thank you. That was actually very correct, and I didn't think of it at all. That yes, they do not have the communication, anything that can communicate. Okay, so the next question is how you used bag of words in the smart device, or how those types of data are compatible with the smart device.
Yeah, so we're not computing any bag of words in the device itself. The device is just providing raw data, which we compute features out of, and then send the features to the cloud. And then all the AI and the machine learning happens by collecting data over multiple patients, and using them for understanding the patterns and then defining the models. Once we have the model ready, then when a new patient data comes in, we can start classifying them. So none of the bag of word models or any of that is actually done on the watch itself. Most of the machine learning is done on the cloud or our servers. And then once we figure out the right features, we create the right programs and upload it in the watch.
Yeah, thank you. Any other questions?
Also, one other important thing to notice is that those devices which you talked about, they don't have a UI. How will you do a cognitive test on a shoe, right? Or how would you dial and say my pain level is 5? Or be able to speak your pain level, and we can use VR to recognize. So those devices are very limited, and that's one of the reasons I was mentioning earlier that our expectation is that the watch is going to be a hub. And nowadays watches are not connected to smartphones. They are standalone, and people are using it without a smartphone.
Yeah, thank you. That was very insightful. Any other questions? No? Okay, then. Thank you everyone for attending the talk. And we have recorded the session, yes, so it will be available on our YouTube channel once the symposium is over. And a big thanks to Sanjay for taking out time to share his knowledge on smart health in spite of being in a different time zone. We have another talk today evening by Alireza Jolfai on Introduction to Cyber Physical System Security at 6 p.m. So I look forward to seeing you all tonight and in the upcoming events of the symposium. Take care and stay safe.
Thank you. Bye-bye.
Thank you.